Hello again. We are doing lecture 19 in this video. You know, it feels funny not to be able to see you or talk to you, just recording these lectures. I'm just hoping that everybody is healthy and safe. Please continue to stay that way. And I just hope that my videos gives you, something to do in these days when you can't do much. Okay, so before we talked about finding power series solutions of differential equations around ordinary points, and now we will discuss singular points, but not any singular point. We need to talk about regular singular points. So I've been telling you this from the beginning. Given a differential equation, in general, it's a very difficult job to find solutions, all solutions, or the required solution. And in this course, we are only considering a limited type of equations where we can develop systematic ways of getting solutions. And within those methods, there are a lot of parameters. And let me remind you how we ended up at this point. First, we consider higher order linear equations with constant coefficients. And then if the coefficients are not constant, but functions of the independent variable, we discussed around ordinary points how to find power series solutions. Because it's hard when the coefficients are not constant, it is hard to obtain explicit solutions of the differential equation. And now we want to discuss certain types of singular points. So first, let's remember what is our ODE, ordinary differential equation, a function px. I think I will stick to small letters from now on. Px of y double prime plus qx of y prime plus rx of y. And we are going to consider the homogeneous equation because we know what to do for if the equation is not homogeneous, we get solutions of the homogeneous equation, and then we use variation of parameters to get the solution. Okay, now remember for an ordinary point, we need to look at the functions. So first, we write this equation in the form we divide by the function px. So remember, to be an ordinary point, the functions, the coefficients q over p and r over p should be analytic at the point x0. So if they are not analytic, then it's not an ordinary point, it's a singular point. So a point x0 is called a regular singular point if. So what are the conditions? So we need two conditions. First of all, it should be singular. If it is a singular point, let's just remember what that means. It means it is not an ordinary point. What does that mean? The functions q over p and or both of them may not be analytic, or just one of them not being analytic is enough. R over P, not analytic at x0. But this is not enough. So this is a definition of a singular point. To be regular singular, we look at the limit as x approaches x0 of x minus x0 times the function qx over px. We require this limit to exist, say alpha. And we look at the limit again as x approaches x0. Now we look at x minus x0 squared, rx over px to be beta. So we require both of these limits exist. So alpha and beta are real numbers, not infinity. The limit exists and not infinity or minus infinity. They are real numbers. So to be a regular singular point, first of all, it has to be singular. I'm going to show you examples. Basically, not analytic. In our examples, this is going to be clear. The functions are not going to be defined at the point x0, so they cannot be analytic. But remember, just for the record, that a function may be defined and it may have all orders of derivatives at a point, but still not analytic. So being not analytic is kind of hard, but it happens. So the easiest way that it happens is when the function is not defined or not continuous or not differentiable. Okay. So, but being singular is not enough. Also, we require these limits to exist. Okay. Now, a quick example. Consider the equation x cubed times x minus 1 times y double prime plus x plus 2 times y prime plus 4y equals 0. Now, the function px is x cubed x minus 1. The function qx is x plus 2. And the function rx is constant 4. So q over p, x plus 2 over x cubed x minus 1. And r over p, 4 over x cubed x minus 1. Now, the coefficients are polynomials, so q over p and r over p are rational functions. Remember what I told you last time, all rational functions are analytic when they are defined. So for rational functions, we look for points where the functions are not defined. And basically for rational functions, it means the points where the denominator is 0. And both functions have the same denominator, x cubed x minus 1. So x0 equals 0 and x0 equals 1 are singular points. At these points, the function q over p and r over p are not defined, so they cannot be analytic. They are singular. And there is no other singular points because the functions, okay, let's also write this down. There are no other singular points because the functions q over p and r over p are rational functions. And they are defined at every x different from 0 and different from 1. Recall, all rational functions are analytic oh, my arrows are not. Oops. Yes. All rational functions are analytic at points where they are defined. Okay, so we have two singular points. Now we need to check whether they are regular or not. So first, let's take the singular point 0. We need to check the limit as x approaches 0 of x times the function q over the function p. So x goes to 0, x times, what is q? The function q is x plus 2, and the function p is x cubed times x minus 1. So if you simplify the x, we have x plus 2 divided by x squared, x minus 1. As x goes to 0, numerator goes to 2, denominator goes to 0, and positive, denominator is negative. So this limit is minus infinity, does not exist. So we don't need to check the other limit. Once one of them doesn't exist, it cannot be regular. x0 equals 0 is not regular. Now we have another singular point, x0 equals 1. So we check the limit as x approaches 1 of x minus 1 times qx over px. So x minus 1, q is x plus 2, x cubed, x minus 1. We can simplify the x minus 1. And as x approaches 1, this limit is 3. So this is our number alpha. So this checks out. The first limit checks out. Now we check the other limit as x approaches 1. Now we take x minus 1 squared, r over p. So as x approaches 1, x minus 1 squared, r is constant 4, divided by x cubed, x minus 1. So if you simplify the x minus 1, we have 4 times x minus 1 divided by x cubed. As x goes to 0, this limit is 0. So this is our number beta. Both limits exist. So x0 equals 1 is a regular singular point. Okay, so 0 is not regular, but 1 is regular for this differential equation. Okay, now for singular points, we only look for power series solutions around regular singular points. Well, not quite power series, because since the functions are not analytic, we cannot hope to get a power series. So we need to change the power series a little bit. How to see how to obtain solutions? Now we consider special types of equations which has regular singular points. So we consider what is called Euler equations. Or sometimes called Cauchy-Euler equations. Okay, so what is an Euler equation? For constants, for constant real numbers, alpha, beta, and the center x0, an equation of the form x minus x0 squared y double prime plus alpha times x minus x0 y prime plus beta y equals 0 is called an Euler equation. Or Cauchy-Euler equation. This is just the name. All right, so this is a special type of equation, linear equation. X equals x0 is a singular point, but it is a regular singular point. And if you look at limit as x approaches x0 of x minus x0 q over p, this turns out to be the constant alpha, and limit as x approaches x0 of x minus x0 squared r over p. This limit comes out to be the number beta. So it's a regular singular point. Okay, now to obtain solutions, to find solutions, we need to consider one of the two intervals, x greater than x0 or x less than x0. Because at the point x0, the coefficient functions, remember the coefficient functions are q over p and r over p. Coefficient functions, remember when we consider a linear equation, the coefficient of the highest derivative should be 1. So we need to divide by x minus x0 squared, coefficient functions alpha over x minus x0 and beta over x minus x0 squared are not defined at x equals x0. So we need to consider the differential equation in the interval where x is greater than x0 or on the interval where x is less than x0. The method of solution is basically going to be the same. So first, I'm going to consider the interval where x greater than x0. This means x minus x0 is a positive number. So x minus x0 is e to the t for some real number t. Any positive number is the value of the exponential function for some real number t. Okay, so we are going to make this substitution. E to the t for x minus x0. So we are going to change the independent variable of the equation from x to t. So we need to find the derivatives of the dependent y in terms of t, not x. So of course we use oops. Okay. Now, y prime, remember, it means derivative of y with respect to x, because in the given equation, the independent variable is x. Now, I want to take derivative with respect to t. So by chain rule, I take the derivative of y with respect to t times derivative of t with respect to x. So dy dt, and remember how to find the derivative of the inverse function. We just take the derivative of the inverse function and take its reciprocal. Remember, e to the t is x minus x0. So x is e to the t plus x0. So dx dt is e to the t. Under this substitution, derivative of x with respect to t is e to the t. So if we substitute it here, we have 1 over e to the t, or e to the minus t dy dt. Now, we also need the second derivative. Remember, second derivative means second derivative of y with respect to x. So derivative with respect to x of the first derivative with respect to x. So again, by chain rule, it means derivative with respect to t of this first derivative times derivative of t with respect to x. But same as above, derivative of t with respect to x is e to the minus t. And for the derivative of, so e to the minus t, and I'm taking now the derivative with respect to t of the first derivative. But the first derivative is e to the minus t dy dt. So I use the product rule. First derivative of e to the minus t is minus e to the minus t times derivative of y with respect to t plus e to the minus t. I'm taking the derivative of y with respect to t and taking the derivative with respect to t again. So second derivative of y with respect to t. So minus e to the minus 2t times dy dt plus e to the minus 2t times the second derivative of y with respect to t. So this is the second derivative. Remember, this is the first derivative. Now substitute into the equation. Now, what is the equation? X minus x0 squared y double prime plus alpha x minus x0 y prime plus beta y equal to 0. Now, remember, x minus x0 is e to the t, so x minus x0 squared is e to the 2t. And y double prime from above minus e to the minus 2t dy dt plus e to the minus 2t, second derivative of y with respect to t, plus alpha, x minus x0 is e to the t, and y prime from the side is e to the minus t dy dt, plus beta y equal to 0. So if we simplify, we have minus dy dt plus d squared y dt squared plus alpha dy dt plus beta y equal to 0. So if we arrange the terms, we have two terms with dy dt. The coefficient is alpha minus 1. Equal to 0. Now you see what happens when you make this substitution. The equation becomes linear, ordinary differential equation, with constant coefficients. Okay, and we know how to solve them, right? We know how to solve linear equations with constant coefficients. We consider the characteristic equation. Okay. So what is the characteristic equation? Characteristic. Lambda squared plus alpha minus 1 times lambda plus beta equal to 0. And solutions, quadratic formula, minus alpha minus 1 plus or minus square root of alpha minus 1 squared minus 4 beta divided by 2. And of course, the solutions depend on the discriminant. What is the discriminant? Alpha minus 1 squared minus 4 beta. So the first case, discriminant positive. We have two real distinct solutions. E to the two distinct real distinct solutions, lambda 1, lambda 2. So the solution is C1 e to the lambda 1 t plus C2 e to the lambda 2 t. But now, what is t? E to the t is x minus x0, or, oh, okay, we don't need that, I'm sorry. So C1 e to the t to the power lambda 1 plus C2 e to the t to the power lambda 2. But e to the t is x minus x0. So if the discriminant, and discriminant only depends on the numbers alpha and beta, which comes from the equation. If the discriminant is positive, we have two independent solutions. Independent solutions are polynomials in terms of x minus x0, not x, but x minus x0. So the solution is a polynomial if the discriminant is positive. Now, if the discriminant is 0, then we have a double root. Lambda equals minus alpha minus 1 over 2 is a double root. So the solution is C1 e to the lambda t plus C2 t e to the lambda t. So e to the lambda t is common, e to the t to the lambda times C1 plus C2 t. But e to the t is x minus x0. And what is t? T is natural logarithm of x minus x0, right? Remember, e to the t is x minus x0. This is positive, so if you take natural logarithm of both sides, t is natural logarithm of x minus x0. So for in case of double root, again, we have the solution, x polynomial part, x minus x0 to the lambda, but it is multiplied by a logarithmic term. We have a logarithmic term in the solution. And the third case, when discriminant is negative. When discriminant is negative, it means we have two conjugate complex roots. Say lambda 1, 2. A real part, let's say number a, plus or minus I times the imaginary part. Okay, the real part is minus alpha minus 1 over 2, and the imaginary part is square root. Discriminant is negative, so under the root, we need to take the negative of the discriminant. So 4 beta minus alpha minus 1 squared divided by 2. Okay, and solutions, remember, for the real part, we have the exponential function, and for the imaginary part, we have cosine and sine functions. So C1 cosine BT plus C2 sine BT. Now, e to the t is x minus x0. So we have x minus x0 to the power a. And for t, we need to put natural logarithm of x minus x0. So basically, if you have the Euler equation, after the substitution, e to the t equals x minus x0, your equation becomes linear with constant coefficients, and you can find the solutions as before. I just listed the solutions here depending on the sign of the discriminant. I'm not going to give an example because the example is nothing else, but what you need to know here is how to obtain, once you call e to the t as x minus x0, how to obtain the first derivative and the second derivative of the function, so that when you substitute into the equation, it becomes this equation. And once you write your equation, you can work it out. But this equation is in t now. Once you obtain your solutions, you need to go back using, oops, I'm sorry. You need to go back after finding solutions. Go back with e to the t equals x minus x0, and t equals natural logarithm of x minus x0. But remember, this is when x is greater than x0. What about the interval where x is less than x0? In this case, x0 minus x is positive. So you replace, okay. For derivatives, you need to be careful. So e to the t now is x0 minus x, but you can work out the details. It just happens that you replace x minus x0 in above solutions. with absolute value of x minus x0. And that solves your problem. Okay, if you want, you can work it out. You may ask, what about this negative sign? Because of the negative sign, we may have some negatives in the derivatives. It may change something. As it turns out, it doesn't. The only thing that happens is instead of x minus x0, we take x0 minus x. So to regard both cases, you can, in general, use absolute value. You need the absolute value here because you're taking the natural logarithm. So in order to take the natural logarithm, you need to know whether x minus x0 is positive or not. But if you just put absolute value, then you don't have to worry about it. Okay, so this is a special type of equation with a regular singular point. Now we are going to use these solutions. We are going to use Euler equation to obtain solutions for other linear equations around regular singular points. And that is going to be in the next lecture. That's all for now.